For today's lesson, we're going to work on a new formula, which is how to find momentum, which ties into Newton's laws of motion, especially with action-reaction forces and Newton's first law of motion. And so you'll need your calculator, so go ahead and find that, and then also your equation sheet. So if you want to take a moment and find those two handouts. So momentum is an equation that works on two variables. So it looks at an object's mass and its velocity. So momentum is something we talk about in everyday life, especially maybe if you are in a contact sport like football. That might be something you talk about a little bit in that sport. And so it tells you that an object, in order for an object to have a lot of momentum, the project or the object, I really should say, if the mass and velocity is large. So the more mass something has and the faster you can get that object up to a certain velocity, the more momentum you're going to get. So when you look at defense, individuals who play defense on a football team, for example, you want those individuals to be larger in size, but the big thing is you also want them to be able to accelerate and get really large speeds out of that mass, and that allows you to be a much more effective defense player. And so if you think about it, if the velocity is zero, meaning the object's at rest, it's not going to have any momentum. So we have our formula, and like I said, if you take a look at your equation sheet, this is the last formula for this chapter. When you write the equation out, we have that momentum. It's equal to, again, our two variables. It's the product of mass and velocity, so that means we're going to take our mass multiplied by velocity. All right, so if we want to change this over to variables, it's kind of interesting. Momentum, we can't use m because it's already used with mass, and we use a lowercase m for mass. Well, unfortunately, an equation in chemistry stole the uppercase m, so we're kind of out of variables to assign it. So momentum is actually assigned a lowercase p. So momentum is m times v. The last thing before I change the slide is let's talk units. Mass, just like before, we want that measured in kilograms. Velocity, remember we're not talking about acceleration here. Velocity is meters per second. That means we have one last thing to solve for. And that leaves us with our unit for momentum as a kilogram meter per second, which is not the same thing as a Newton. A Newton relies on acceleration. Acceleration is meters per second squared. So momentum kind of has a funky long unit of a kilogram meter per second. So we have a couple examples to work through with this equation, and like I have done all along, we're going to use KFPS charts. So this problem is asking which has more momentum, a golf ball or this bowling ball. So we have kind of two problems to set up in this particular problem. So we have here, for our K, I'm going to go ahead and start with the golf ball, and it tells us that the mass is 0.046 kilograms, and we know its velocity, that is 60 meters a second. And we want to know which of the two objects has more momentum, so in this particular problem, my P, my momentum, is what I do not know. My formula, I can go ahead and substitute that in for both parts of this problem, and that is momentum is equal to our mass times our velocity. You can go ahead and plug in. We're going to plug in our mass of 0.046 kilograms. Don't forget that unit. And our velocity is 60 meters per second. And then solve. I'm going to go ahead and set up the other problem, and then we can talk about answers here in a second. So then we have our other object. I'm going to switch colors so we can distinguish the two. So we have this bowling ball, same idea. Our mass is 7 kilograms. Our velocity is 6 meters a second. And same thing, we want to know its momentum. So the formula is redundant. Substituting in, mass of 7 kilograms, times our velocity of 6 meters per second. So if we run these through on our calculator, we can go ahead and get our answers. So for this first one, when I multiplied it out, I got an answer of 2.76 kilogram meter per second. My other one, 7 times 6, is going to give me 42, and that's also momentum, so it'll be kilogram meter per second. It wants to know which one had more, so the bowling ball definitely had way more momentum, and the big thing that helped it with that is that its mass was significantly more than the momentum, or excuse me, not momentum, but mass of the golf ball. Now this next particular example in the notes, I'm not going to worry about answering because I want to save us time and save your time. So it's kind of the same thing that we just worked on. So jumping ahead to example 7, we have this marble. It's rolling at a velocity of 1 meter per second. So right off the bat, I know in this example that my K, to start out with, I have a velocity of 1.5 meters a second. And then it says it has a momentum. Remember, momentum is the variable P, not M. And that is going to be 0.1. And the unit there, we can see the kilogram meter per second. And it asks, what is its mass? So this is where that formula sheet, again, comes in hand. I have it attached to the assignment, so if you need it, you can access it there. Otherwise, you can print it if you need to. If you can't, save it. Otherwise, if you, again, want to get your hard copy out, that's going to help you. So when you look at the handout, your formula for finding mass is going to be that mass is equal to the momentum of the object divided by its velocity. So I can substitute in, my momentum was the 0.1 kilogram meter a second. And this is my plug-in part of my KFPS chart. And then I'm dividing it, again, by the velocity of 1.5 meters per second. Solve it out. Our answer is going to be relatively small here because we're working with a very small momentum and not that large of a velocity. So we get an answer of 0.067. If you take a look, meters per second is in the top and bottom. Your handout sheet works through that as well. So the unit here for mass is going to be the kilogram. So we have one last example to take a look at, and that is looking at this bird. And so it tells us that to start out for our K part, that we have this bird with 0.04 kilograms. That unit kilograms tells me that is its mass. And it tells us that it flies with a momentum of 0.76 kilogram meter per second. So momentum is the P part of the equation. And the last thing is the most important piece, is it's asking what is the bird's velocity. So we're finding the speed. So again, we can access our formula sheet. For velocity, you get V is the momentum divided by the object's mass. Go ahead and substitute in. So we can plug in 0.76 kilogram meter per second. And then we have a mass of 0.04 kilograms. So we're going to go ahead and solve. So we take 0.76 divided by 0.04. We get an answer of 19. Again, think back to our days of conversions. Kilograms is in the top and bottom. Those eliminate. So then we're left with meters per second, which if you look back, we're solving for velocity. So that makes sense in terms of what unit we should have here. The last thing, and I'm hoping we can try this out to do a lab that would be done on a computer anyways, is to look at how momentum is conserved. A lot of times this is really useful in physics, and especially in car accidents, is that there is a transfer of momentum. And so if you remember Newton's first law of motion, that an object at rest wants to stay at rest until acted upon by an outside force. So for example, if you take a look at cart B, or example B of the carts, I should say, before the collision, that green car isn't moving at all, and the blue car is moving with 10 meters per second. If you take a look after they have collided, this is called an elastic collision, and so that momentum is transferred, and that object had a force applied to it, and it now has the same momentum as the blue car before it collided. And so that's the same thing that kind of took place in example A, is their momentums transferred from one another. So this is called the law of conservation of momentum. And so the total momentum of a system doesn't change. And so the momentum that you have before and the momentum you have after is the same. So like I said, I'm hoping we can try out a link, and we got to see if it works on your guys' computers before we do anything more with that. But it'll investigate how momentum works in car crashes.